Hi, good afternoon, everybody. Welcome to our first tutorial on MIL standard 1580C. It'll be primarily presented by Rachel Garcia. Rachel is the lab manager up here in Albuquerque for Integra. We have a DPA and a failure analysis lab up here, and she manages the DPA portion of the lab. Rachel is a hands-on engineer, so she knows quite a bit of the various processes that we're going to be talking about during this webinar or tutorial. A lot of the material we have presented before, the difference on this one is that we are going to allow for questions and answers on a real-time basis. So if you have a question, please send us a note on text through chat, and we'll be monitoring the chat very frequently. And when that happens, then we will we'll unmute you at that time. Right now you're muted. Please unmute yourself, and then we'll also unmute you at that time, and we'll have a real-time live discussion for the question that you have. Again, in the past, we have said, please, to go ahead and hold your question. This time, we're not asking you to hold the questions. You can ask the questions as you go along, and hopefully we'll have a good interactive tutorial session. It's an hour and a half long, and I expect that it will take all of the hour and a half because of the question and answers in between. And just as a preface, in the past, we used to do webinars. Webinar was a one-way street. We presented it, and at the end of the session, we asked for Q&A. But in this, again, the difference this time is that we'll try to make it as interactive as we can. And we are really focusing on 1580C, which has been implemented for almost a year now. So without further ado, I welcome everybody, and we'll have Rachel start the tutorial. Can you guys see the slides? Maybe one of you can send me a chat so that I can see it or I can hear you.
Awesome.
Okay, thank you. And perfect. Thank you very much. Appreciate it. All right, let's get started, Rachel.
All right. Thank you for the kind introduction, Sultan. We have a lot to cover with DPA, so let's go ahead and get started. Go ahead and go to next slide, Lo. All right, so let's talk a little bit about DPA. DPA, destructive physical analysis, is the process in which a sample size of components are examined using non-destructive and destructive testing techniques. During DPA, we inspect for various design, processing, and manufacturing defects or anomalous conditions that may cause a latent failure. Notable standards are listed below, as you can see on the slide. The most common standard is MIL standard 1580 Rev C, as Sultan just mentioned. Next slide, please. Within MIL standard 1580, several test methods exist for certain types of commodities. You can see MIL standard 202 is usually used for passive type devices. MIL standard 883 will reference criteria for microcircuits. MIL standard 750 will cover transistors and diodes. And MIL standard 981 will cover magnetics such as inductors and transformers. Thank you, sir. All right, so let's talk a little bit about commodity packaging. Hermetic and plastic packaging are the most common types in the industry. Hermetic packages are usually made of metal, ceramic, or a combination of both. These are packages such as TO cans or ceramic dip type packages. In contrast to hermetic packaging, plastic packaging uses organic materials. The advantages of using plastic packaging is cost, size, and weight. And you will see now in the industry, we have a ton of plastic components going through. Next slide, please. Let's talk a little bit about the basic DPA flow and how it's processed through the laboratory. Once components are received in-house, all relevant paperwork, such as the PO, the data sheet, and customer statement of work are reviewed and built to make a checklist. The checklist is built based on the commodity and type of packaging using a combination of non-destructive and destructive techniques. You can see up on the slide here, some non-destructive testing would be external visual, real-time X-ray, XRF, PIND, or acoustic microscopy testing. Some destructive techniques would be mechanical, chemical decap, bond pull, ball shear, SEM Metallization Inspection, cross-section, and scribe and break. Those are just to name a few. Next slide, please. You don't have anyone asking questions yet?
Not yet. I'm monitoring it. There are questions coming in on certain things, but no.
Okay, perfect. Thought I would check in. So let's talk about external visual. External visual is a non-destructive test technique. It's typically performed at around 10x magnification. The actual performance spec of the part will tell you which meg is best to look at external visually. The package conditions, such as the leads, the markings, and seals, are thoroughly inspected using a microscope. We also document the markings and the package condition at this step and include it in a final report for review. Next slide, please. The next non-destructive technique I want to talk about is X-Radiography. This inspection is extremely useful for examining the internal construction of a device non-destructively. As you can see in the images below here, on your right-hand side, you have a broken bond wire. This was seen non-destructively in X-ray. Had we decapped prior to doing any X-ray, we may have thought that we would have induced that broken wire due to delid processing. But because of X-ray and the non-destructive technique, we were able to identify it prior to doing any destructive technique processing, which is great. On your left-hand side there, you can see a plastic encapsulated device in which the bond wires are sagging below the imaginary plane of the silicon die. This is a failure criteria per MIL standard 883. And again, we caught it in non-destructive technique X-ray. Had we done chemical or laser ablation prior, we may have thought that we induced that during chemical decap. But again, because of non-destructive techniques such as X-ray, we were able to see it prior.
There's one question.
Sure.
So it says, this says, does DPA happen before or after any screening or qual steps, or is it not related?
Well, I think this is kind of your alley, Sultan, but there are several DPAs, if I'm not mistaken, within a qual. It just depends how in-depth that qual is.
So, and Rachel is right. So technically you want to do a DPA at the start. If you are doing a qual, if you're doing a screening, technically you want to do a DPA before any screening of the qual starts. And the purpose of that one is because you really want to know if this lot is any good or not. DPA will tell you a lot about the manufacturing process, both from the assembly and fabrication process, and even in some cases, just fundamental design issues or something like that, especially when you're looking at the reasons why there are CT mismatches and the likes of it. Typically also, if DPA is required, not only pre-screening DPA is done, but in a lot of cases, post-qual DPA is also done.
Yeah, I think you covered it. All right, so Sultan is queuing up a video now. What we're showing here is a technician that's setting up for real-time X-ray. You can see the technician placing the parts in the tray within the system itself. Once the parts are set up, she'll close the door and we'll start with real-time X-ray. This is much different than film X-rays where we don't have to go to do that process anymore. So digital X-ray is totally our friend these days. All right, you can move on, my friend. All right. So moving on to particle impact noise detection. Again, this is a non-destructive technique. The short word for it is PIND. PIND is used commonly. PIND is performed on hermetic devices to detect loose particles within a device cavity that may have been trapped inside during manufacturing. Several methods of detection are available, the O-scope being one, the audible speaker being another, and the threshold detector being the last one. If you want to play the video there on the left. We'll talk a little bit about PI&D here. There you go. So in here you can see on the screen, you can hear the rattling around. This is essentially a particulate that's within the cavity that's being captured through the audible, through the O-scope, and what you're not seeing on the screen right now is the red detector light. Now if you play the next video right next to it, this is what we would consider a passing device. The O-scope is clean, there's no audible noise, nothing rattling around in there, and that's what you would expect from a passing device. PI&D is performed to 750 and MIL standard 883, and to be clear, it's only performed on cavity type hermetic devices. This test is not performed on plastic devices.
So Manny's question is, apologize, but why is this not conducted on PEMs?
So PEMs are fully encapsulated devices. They're fully molded. There's not a cavity for something to rattle around, if you will. So that's why it's performed on hermetic devices only. Hope that got you, Manny. Alrighty, so moving on to prohibited material analysis, commonly referred to as PMA. PMA is performed using XRF or EDS. Typically, PMA is performed externally on features such as lead finishes, lid sills, and terminations. 1580 Ref C now includes internal PMA for certain commodities. And you'll be looking at things such as die attach, lead frames, posts, and bonds. So typically, internal PMA is performed utilizing EDS. Externally, we prefer to use XRF. And you can see here on your screen the output from an XRF machine. You have your spectra there on the left showing the elements. And then on the right is an image of what we analyzed and the weight percentage of the elements. MIL standard 1580 requirement 9 is what's driving this. Next slide, please. Oh, got a video. So here's a video of one of our technicians performing XRF testing. XRF usually performs at around 50 kV. EDS, we can shoot at around 20 kV, so you'll get a difference in elements there. That's usually the main driver between the two machines in itself. So you got the tech that put in the part, went ahead and it's going into the machine, it's closed off, and you will see the part here in XRF, and he'll start to analyze. Any questions there?
Yeah, there's a question. What is the criteria for selecting XRF versus EDS? When would you choose one or the other?
Sure, great question. So as I mentioned, XRF, we like to do that externally before the part's delidded or decapped, because we're able to get bigger, larger items, you know, like the lead finishes and, you know, the lids, the package material itself. Internally, it's our preference to perform EDS. It shoots at 20 kV, and we're really good to get platings.
I think I just got disconnected again. I don't. Your internet has kicked me out again. Okay. Can you find it? Can you guys hear us?
I hear you, Sultan.
Okay, perfect. Thank you.
Good.
Go ahead.
Okay. So XRF externally, leads, lids, package material. Internally, we prefer to do EDS. You're looking at things such as, you know, the die attaches, the bond wires. You can look at bond pads. So XRF externally, EDS internally is our preference.
And the other, I think one of the other differences is the depth to
Yep.
which the ray penetrates. In one case, I believe the XRF, EDS gives you a deeper penetration versus the XRF penetration. So you're able to get a better granularity if you do EDX versus the XRF.
For finishes, you're correct.
Yeah, for
because
finishes.
XRF shoots at 50 kV, it's likely that you will get underlying materials within your finish. If you're doing EDS and you're shooting at 20 kV or 10 kV, you're surely getting the finish there, as opposed to any underlying materials.
Perfect.
All right, seal test. Did I answer all the questions for XRF? Perfect. All right, so hermetic seal testing, also known as fine and gross leak testing, commonly performed with hermetic type packages. Again, it's just hermetic packages that go through seal testing because they have the cavity. Several test methods are available for seal testing. You'll have a helium fine leak test, perfluorocarbon gross leak testing, or radioisotope KR85 type testing. KR85 testing offers several advantages over standard helium testing, the most notable being quick turn times. We prefer krypton. It's quicker, faster, easier. Helium will take a little bit longer to bomb, and that's dependent on the device cavity. What we have here is we have one of our managers showing our KR85 test setup, bomb chamber, if you will. The area to the right there is the chamber. We put the parts in and we go ahead and bomb them with the krypton. And then they come out and they essentially have a sniffer that we're looking at to see how much krypton is leaking. We still good?
Yeah.
Okay. Moving on to scanning acoustic microscopy, otherwise known as SEM or AM. SEM is a non-destructive test to find delaminations, voids, or cracks that can sometimes occur in plastic packages. SEM uses sound and transducers to capture an image of the device. Suspect delaminations or voids are usually indicated by red pixelations. So these are some great examples up on the screen. On the lower right-hand side is the backside scan of a device. The red pixelation in this case is indicative of true delamination. When we look at the parts optically, and you can see that on the image on the top right, you see some bowing, if you will, of the plastic, some warpage of the plastic. We saw that again in the top side scan, in which you see the red pixelation through the top of that lead frame. Again, SEM is a non-destructive technique and it's used for plastic components. We have a video here showing our SEM in action. Although what you're not seeing here in this video are the parts that are down in the bath. The bath acts as the conducer for the transducer. And what you'll see there is the image start to be produced on the right-hand screen there. So do you want me to I'll stop there and get questions?
Yeah. Venture someone, there's quite a few questions on that.
Perfect.
Let's see. How does CSAM differ, is different than SAM?
It's not, it's the name, right? So SAM is scanning acoustic microscopy. Then you have what's considered C mode scanning acoustic microscopy. Those acronyms are used very much in the industry.
It's the same.
It's the same.
And then there's a question, has moving to J standard 020 relieved some of the pass fail criteria previously in 1580? Recall the J standard 020 being a little bit more lenient on delaminations. I can answer that if you want.
That's a great question because we talked about that earlier today, my friend.
Yeah. So Tim, the previously 1580 had its own criteria. What J standard 020 has done has taken some section of it and said these items within the 1580, the previous 1580 is non-negotiable. If you have failures on top of the active die surface or the likes of it, it is a failure. And then there were certain criteria that J standard used to say, for these ones you need additional data. Just because you have delamination on lead fingers does not mean it's failing. You need additional data, you need additional validation. If the additional data or the validation says it is not a failure, then it's not a failure. MIL-Standard 1580 wasn't that flexible, but ever since they've adapted the J standard 020, there's a flexibility, and yes, it will allow us to reject or have more of a dialogue with the customer than what we previously used to have. So it's a good question.
Well, and to add to that, we're still talking about combining the 1580 and 20 to make it more easy, readable for the user.
Absolutely. Another question. Why should someone reject parts based on voids for PEMs? Is it voiding on top of the die, or does it really matter at all if the parts pass screening?
So and I know you know a lot about this one as well, and there's a few factors that come into making that type of decision. It's dependent if the, dye penetrant test is good to validate, and that's something we'll talk about next, but to validate what we're seeing in CSAM. In cases, SAM is going to show delamination on the top surface of the die. There may not be a path for moisture, so it may not be a concern, but it may be a concern for the packaging folks and how it's going to act in reflow. But a lot of the qual testing that, Sultan and these folks do, if electrical testing is ruling it out after several quals and several tests, the data is there and a better decision can be made.
Absolutely.
I don't know if you want to chime in on that.
No, the only other thing is, please go to look at J Standard 020, 6.1, 6.2. It clearly says, very first sentence, delamination, and call it a void, is not necessarily a failure. You need additional data, and Rachel rightfully stressed the fact that if you are suspecting that this device may have a real delamination, then do a dye penetrant test. So that's all I have to add, but if you have further questions, obviously I'll take it. One more question. Are devices identified in SAM as with delaminations that definitely rejects, or some reliability assessment is required to determine it? And I think we just discussed that. There are certain criteria that is non-negotiable. If there's a delamination on top of the active surface, again, MIL standard 1580 tells you which one it is. J standard 020 tells you what it is. But there are certain criteria that are negotiable. That falls under get me extra data. Let's see. I think that's all the questions I have on. Let me go down. Last question. Can SAM be used on ceramic parts?
So not ceramic parts with a cavity. If you perform CSAM on a ceramic part with a cavity, you're going to get essentially a black image because there's basically an air gap for our transducer and the noise to travel. So you're not going to have anything there. If it's a ceramic capacitor, a stacked capacitor, those CSAM is performed on those here and there in the industry, but you're not going to get the full depth of the capacitor stack. You're only going to reach a certain depth to look for voids. So if you have a hermetic package, no, CSAM will not work. If you have a ceramic stacked capacitor, it can work, but it may not get to the depth you need it to.
And it's the physics of acoustic microscopy. When the ray, when the ray comes down, or the beam comes down, it is, if there is no reflection, if it can penetrate to a certain level, no problem. Ceramic, or in a lot of cases metal, is when the acoustic wave cannot go any further than the material itself allows you to do that. So it's a little bit tough, hard. That's it. I think we should move on to the next subject.
Fair enough. And it ties into CSAM. So the next subject is dye penetrant.
There's one more question real quick. They said, can void be seen in real life X-ray? And the answer is probably not. It doesn't have the level of depth that there is. I would say greater than majority of the cases. In some cases you will see it, but the kind of acoustic microscopy type voids, a delamination or the likes of it, no, you cannot see that in X-ray. If it is a gross crack or something like that, yes, you will be able to see it in X-ray.
Yeah, if it's gross enough for PEMs, you would see it in X-ray, but it has to be gross.
It has to be gross.
Yes. Okay. Okay, so moving on to dye penetrant for PEMs. As Sultan mentioned, J Standard 20 talks about maybe doing some additional tests to vet the reliability of the component after SAM testing. What we suggest and what's commonly used and called out in MIL Standard 1580 is a dye penetrant test. Dye penetrant examination is usually performed to verify those SAM findings. As you can see here, you have your CSAM image that's at the middle of the screen. The red pixelization is indicative of some delamination. The two images on the bottom of your screen are what we consider dye penetrant images. You'll see the lead fingers coming into the molded package, and the bright UV, the green UV coloring that's right by those lead fingers are proving that there was a delamination there, and the dye did penetrate in through that lead ingress and is now being fluoresced by the UV lighting. This is a great technique to prove out what you're seeing in SEM. SEM can be subjective, there could be water ingress and many other things. So it is sometimes very good to do a dye penetrant. As I mentioned, it's called out in MIL Standard 1580 Rev C. Any questions on that guy?
No.
Okay, perfect. So moving to mechanical decapsulation. Mechanical decap is different from chemical decap. Mechanical decap is the process of removing the lid of a hermetic device. For TO cans, a can opener tool is used to cut around the base and remove the lid. A typical type of TO can is seen on your right-hand side there of the slide, the top image to your right. For SIR dips, these packages are usually dry grinded until the cavity is reached. So we have a SIR dip is your middle image there on the bottom of the screen. We grind through that ceramic and expose the internal workings of the device. And then we have metal lidded devices. We essentially use a sharp razor to slice through the lid attach and remove that top lid, if you will. The bottom right-hand image is showing a device in which the metal lid was removed. Thank you. And so moving on to a part of processing for chemical decap. Before we move to chemical decap, we start with a laser ablation process. Laser ablation is a great technique used before chemical deprocessing. With laser ablation, several layers of plastic material are removed. This process will dramatically reduce the chemical exposure. It will significantly help preserve the internal bond wires and any internal platings that have been exposed. And it especially helps you get where you need in terms of copper bond wires. What we're going to show here is a little video of laser ablation. In the chamber itself, in the Follett chamber, we have the device. At this time, the technician turns on the vacuum to pick up all the additional residuals that are being ablated. On the screen there, he's showing the device of interest, and now it's showing what is being lased. So at this point, he created a map of what he wants lased, the material he wants removed. He creates a cavity or a trench and prepares it for chemical processing. So moving on here to some chemical and laser ablation. So we have some SIM images of a copper bonded device. This has many, many wires, many copper bonded wires in here. What we did is we laser ablated several different areas, created several different cavities. We mixed in some chemical deprocessing, and you can see that the integrity of the copper bond wire stayed well intact for this type of device. This is the plus of having laser ablation. And here's the final product, optical imagery of some chemical decaps that we've done. So after laser ablation, we can mix some chemicals. It could be nitric sulfuric, a combination of both, or one standalone. As mentioned, we create the trench or the cavity. The acid is applied, and we apply enough acid so we can expose the internal dye and as well as the bond wires. So on your top right-hand side image, you can see a small SOT23 copper bonded device in which the dye is exposed as well as the copper bond wire. Same thing goes for the right-hand image on the bottom right-hand side. That's a copper bonded device with chemical processing. And then on the image to the far left, you have a gold bonded device, and the image in the middle, you have an aluminum bonded device. All of these devices went through laser ablation first and then chemical processing. Got a question?
Yeah, it says, can you use chemical decapsulation for copper bond wire?
Yes, and it's awesome to do that.
However, you really want to, it's an acquired skill. So if you have an extremely good lab technician who has done day in, day out this kind of work, yes. But But in order to be a little bit safer, or quite a bit of a safer, you really want to do laser ablation. Before laser ablation, there was nothing but the manual chemical decap anyway, for years and years and years. And we did it. Everybody else did it. So, yeah, can it be done? Yes, it can be done.
Is it easy? No.
That's not it.
Yeah, you really got to fine tune that process. Cleaning it up, getting what you need, that's the fine tuning of it. But laser ablation helps you greatly with that process.
Only problem is that you can take a part of the gold wire, dip it into the acid, leave it up there for a minute or two, and you're done. No harm done. The wires are still intact and the likes of it. While in case of laser ablation, you have to, the first process is take an X-ray, superimpose it over with a laser machine, and then you start to ablate it. You ablate it to maybe at 80% level, take the part, do some more acid etching, look at it, see has it gotten to the wire or not. Do a little bit more acid etching for another 15 seconds. So the process it takes to decap a device could take as long as 4 to 5 minutes per device, depending upon what are you trying to do with the process. So, couple more questions for you. For all these techniques, how much dose is accumulated? I don't think so there's any dose accumulated because of the laser.
No radiation dosage, no.
No radiation dosage.
No, it's what's integral is making sure your laser settings are accurate for your part type. You don't want to overheat your part by applying too much laser ablation.
And for the X-ray machines and the likes of it, whatever we use in our lab, there is OSHA guidelines to how much dosage you can have in that lab for human safety and all of the safety. So we follow all of those OSHA guidelines.
Yeah, through dosimetry.
And this you may want to address a little bit later. Is destructive wire pull required on PEMs? And you can do it on the PEM section.
Yeah, it is. And I'll cover that too.
All right.
All right, so here's a quick shot of our chem lab. This is after laser ablation processing. Our technician has set up the wet lab, the chemical wet lab area, at which point they're gonna pick which acid they wanna use. They create a fresh batch and they apply the acid. Here you can see some acid mixing that we may be doing a dip out process on. All right, so internal visual inspection. So this testing is performed once the internal construction of the device is exposed. So right after delid or chemical decapsulation, we are going to perform an internal visual inspection. At this point, we're going to be looking for a number of possible defects. You're looking at glassivation or passivation type defects, bond wire defects, bonding defects. But also at this time, we'll take the time to document the die itself, capture the markings, make sure that they're compliant to the MIL standard, and move forward that way. MIL standard 750 and MIL standard 883 are typically used for these types of internal visual processing. You can skip this video. Thank you. So scanning electron microscopy, otherwise known as SEM. After we do delid and internal visual inspections, we move to what we call the SEM inspection. At this point, we're documenting the internal cavity of the device, the internal construction of the device if it's a plastic component. We're also looking at the bonds, something that you're not able to see optically. You can see down here in the lower left-hand image, you can see a bond that's sitting on the bond pad, but the metallization around it has been attacked. This is something that we didn't see very well optically. So once we put it in the SEM, we got a great image of what was going on there. The image right above that is showing the side of the die optically. We did a great internal visual inspection. We didn't see anything anomalous with the die. When we put it in the SEM, you can see that the die was cracking away there at the base and ended up getting trapped into the gold silicon die attach. It doesn't have a chance really to break away, so it was a concern here, but we were able to document it and include it in the report. So an SEM inspection after decap and before wire pull is great.
Question, how do you remove the glassivation?
Sure. So there's a couple of different techniques. MIL standard A83 2021 gives a couple for when you're doing glassivation type testing. It depends on the type of glassivation applied. So you can have a nitride. You can have different types of glassivation, and you'll want to use a different type of etch. I would suggest looking in A83 test method 21, I believe, for glassivation. And it gives a couple etches if you're looking for aluminum metallization. And that, I mean, that's to look at glassivation to make sure if the glassivation's intact. You really need to pull out the books to get the glassivation removal techniques.
It could be chemical, it could be, it could be chemical, you could use plasma, you can use an argon for a gas for plasma, you could use other gases for plasma. Depending upon, for typical DPA, is a chemical glassivation removal that happens. But for failure analysis purposes, there are other techniques that we use.
Yeah, and I think I got the glassivation test and his question kind of mixed
Yeah,
up.
that's
So
right.
yeah, thank you for that. But to remove it, you're right, you do use a reactive ion etcher or plasma, and then you can use chemical processing to start removing that glassivation to start inspecting for your metallization layers.
Thank
All right. So we're going to show now a quick video of typical SEM. So this one doesn't have anything on the screen, but this is the SEM room. What we have here, you can actually kind of see something come up on the screen. You can see the chamber. We go ahead and evacuate the chamber, put the sample in, and we're able to get an image up on the screen. Usually SIM can take you up to 350,000 times X for types of inspections. Right, so moving on to wire bond pull and wire bond shear. Both are performed to evaluate bond strength and integrity. The method in which the wire breaks or shears is very important for DPA analysis. For example, the left-hand image of a ball bond lift indicates that the bond had a weak, non-uniform intermetallic prior to pull testing. The right-hand image shows the result of a crater-type shear, possibly an indication of overbonding. Both are bonding type anomalies. Next slide, please. Go ahead and show this video. This one's pretty good.
There's a question. The first question was, do we do destructive bond pull at PEMs?
Yes.
And obviously, you said yes.
Well, if you're doing a DPA to MIL standard 1580, 16.5, it will require you to do the destructive bond pull.
And the other question is there a min limit for the copper bond wire test, or is it reference to gold wire
Great.
bond?
That's a great question. So coppers now with the 1580 revision C, they are to be treated as gold.
That is correct. There is a independent requirement by some customers that says that you need to have a 2x the goal. So you will occasionally hear somebody says it's 2x because it is required by certain customers. If you just purely go by MIL standard 1580, then Rachel is right that it's 1x. We are developing. I'm a member of Gold Wire team that's led by Jeff Jarvis. He's the lead. I'm his co-chair, and JC14 is also working on it. And Curtis is establishing the methodology, but Jeff's group is then going to establish the criteria. Not only will it be an absolute number, but it will also be some statistical methodology will also be used by the time the new criteria is established.
Yeah, 2x gold was being commonly pushed through the AEC, and it's still being used.
It's still being used.
Yeah. All right, so die shear testing. Die attach integrity is tested during die shear testing. Force is applied to the edge of the die, the longest edge of the die, until the die breaks or separates from the area that is being inspected. So on the lower right-hand side image is the silicon die that has already been sheared away. The left-hand side of it is what it looked like prior to shear. So you can see that the silicon remained intact to the gold silicon die attach meaning it was well adhered. If the die were to pop off with little or no force, we would have some concern, and it would more than likely fail the MIL standard DPA. SEM Metallization Inspection. So this ties into the gentleman that asked the question about the glassivation. To do this type of inspection, the glassivation does have to be removed so we can start looking at the metallization structure itself. At this point, you're able to look for any collapse of the wire, of the SEM metallization line, or any kind of contacts that have thinned out and are not meeting the requirement for 20% fill. Again, this type of inspection is done first chemically, remove the glass, and then we put it into the SEM to do an in-depth inspection. So moving on to cross-section. Cross-section is performed on several different commodities for internal inspections. For instance, diodes are cross-sectioned to look at the die attach placement. You can see that in your left-hand side image. The middle image there on the bottom of your screen is a ball bond, a gold ball bond in cross-section. We look at intermetallics optically, and then we'll throw it in the SEM to look at the bonding there. And then capacitors, you can see that on the right-hand screen there. You can see the electrodes and the dielectric capacitors are commonly cross-sectioned per the EIA 469 standard. So many commodities can be cross-sectioned and great value to that. So I think I've covered all that testing. Lo's going to show a video now of cross-sectioning in process. Here we kind of call it rocking the turntables because you have a cross-section, and as you can see, the technicians there kind of grinding into that part until the area of interest is achieved.
So basically the part is embedded into a glass material, if that's what you're going to call it.
An epoxy, yeah.
An epoxy. And then at the bottom of that little thing is the die, and it takes a little bit of the die surface out at a time.
The package surface.
The package surface. And again, it's a technique that it's a learned technique. It's not an automated technique that you could have. So
yeah. So I'm going to stop there. We've covered all the testing, and now we're moving into why perform DPA.
So there's a question about, so there's one question and there's another related question up there. Do you believe that copper bond wires are good as gold wire for parts moving into the future?
Oh, that's a trick question. In my opinion, I don't know if there's enough established reliability criteria, white papers, yada, yada, to say if one is better than the other.
No, I'll add to it is that there is not a process maturity for copper bond wire amongst all suppliers. So the level one suppliers, level one being the one that make billions of devices a month, versus level 2 and 3, there are people who make maybe a few million pieces a year or the likes of it. What we see is a maturity difference between level 1 and level 2. What we also see is equipment variation. The gap is narrowing, but do we see copper bond wire failures? We do, both at DPA and during quals and the likes of it. And in case of gold wire, because of gold wire bonding process, we have not seen any failures over years. Maybe that voiding issues that we see intermetallic between gold and
it's sporadic.
Very sporadic. While copper bond wire occasionally we will see that. So one is sporadic, one is occasional. So is copper bond wire a future? Whether you like it or not, whether you believe it or not, it is our future, and the future is here already. So the other question that they had was, question is when do you perform DPA and when do you perform construction analysis?
So for us, that's usually driven by the customer. Customer will say we want the DPA, or we found an issue with the DPA, so we want to do a construction analysis. In some cases, you know, folks are trying to vet a new part for a new design. If that's the case, their engineers will want a construction analysis to look at the changes of that device over time and how it's going to play a part in their system. So it's truly driven by the customer. We can give some guidance based on what they're seeing, but it's based on their end application.
So if you look at the AS6294/1 and /3, which is one for space and one for military, for PEMs, we clearly establish in that spec that when it is a new product, it's not necessarily new technology, when it is a new product for a mission that you have never used before, you have not a lot of pedigree or information about the part, then construction analysis is the first thing you want to do. Construction analysis goes a little bit deeper than DPA. It does more layer by layer analysis. It also does more material analysis in terms of what material are you using for assembly. So construction analysis has got additional steps that is not available in DPA. Construction analysis also points out to some basic manufacturing defects, like is this even the right way of doing a die attach? Is there a CT mismatch because of the way you do the die attach and the likes of it? So construction analysis you want to do if it's a new process or it's a new something for your work that you've never used that part before. Otherwise, DPA is nothing but a QCI testing. You have this lot, you want to do screening, you want to do qual, and you want to do a QCI testing, and DPA just tells you this lot has some basic fundamental defects or not.
And if I can just add something, the cool thing with MIL Standard Rev C, they've now added in criteria for construction analysis, which says, you know, pick and choose which tests you want out of the MIL Standard and create your own construction analysis. So if you do want to send something out for a construction analysis, you can reach out to guidance from the DPA house on how you want to proceed with your construction analysis using military standards, which is a great addition.
You can use 1580, 38534, 38535, has got tables for new technology evaluation. And if you want, so it's outside of what you would do for screening and qual. So look at the tables for technology on 38535 for 38534 and say, how would I better my knowledge for this technology, for this type of a test that I need to perform. And for that one, you would reach out and say, hey, I want to do a construction analysis so I understand the physics of failure for that specific test.
Yep. Do you have any more questions?
No, move on.
Okay, all righty. So why perform DPA? $1 million question. Go ahead and go to next slide there. All right. Well, here's a good reason. During electrical testing, we experienced several failures. Using X-ray, we were able to detect broken or misplaced bond wires, as well as extraneous bond wire material. So what you can see there on your left-hand image is on the top side, the bond wire is not connected at all. You can also see this through the side view in which the arrow is pointing to. On the right-hand side image, it's an extraneous bond wire material that was left in the plastic encapsulated molding compound. You can see it running across several bond wires in the top side view. In the bottom side image there, you can see it in the side view, kind of floating around, if you will. It's truly embedded in that plastic molding. Here's another reason. So overbonding. From the image on the left, you can see the bond wire is a bit long and it's overhanging the neck down area of the ball bond. In the right-hand image, the passivation surrounding the bond pad is severely cracked and excessive aluminum splash is seen around the ball bond, indicating that possible overbonding took place. Now this is a good one. So this is a cracked hill of an aluminum bond. In SEM inspection, you can see that image on the left-hand side. You see a crack that's going through the heel of the aluminum bond. When we went to go do bond wire testing, bond pull testing, the bond ended up breaking with little to no force. And it also broke or fractured where we first noticed the crack in SEM inspection. Had we not put this part in the SEM, we wouldn't have captured that image prior to doing the wire pull. So we kind of got lucky in that sense, but this is why DPAs performed.
Question.
Sure.
Couldn't some of these defects be detected at post-bond visual inspection?
So post-bond visual.
So he's talking about when you do, when the manufacturers do the bonding, there's a visual inspection up there.
So not visually, if they had done 100% X-ray screen of that lot for X-ray, they would have caught it. And it's a non-destructive screen, right?
Right. Right.
So that's the good thing.
Okay,
So,
that's an excellent point. It's a non-destructive screen, so you get what, yeah.
So in this case, had we saw this in DPA on the small subset of parts, we notified the customer and they went back and screened their entire lot non-destructively. So what's on screen now is a great example. This is one of my favorites. So on your top left-hand side image there, you have a CSAM image or a SAM image. The red pixelization is right around that lead frame. It looks pretty gross. We weren't quite sure what was going on. You can see that we put this in cross-section. We also did a dye penetrant, but in this case, we didn't need the dye penetrant because you can see the large voiding there where the die attached fillet should have been. All right, so moving on, solder ball between the windings. So talking about how great X-ray is, the top two images, you have our X-ray. We saw a faint shadow that appeared to be possible extraneous material. We cross-sectioned to the area of interest, and as you can see, the extraneous material was found to be a solder ball that had found a home between the two coil wrappings there. EDS can be performed at this point, and we were able to determine that it was actually the lead attach that had found its way into that cavity there. Next slide, please. So as good as X-ray can be and how great of a powerful tool it can be, there's some materials that are harder to inspect than others. This is a great example. This is a device that uses gold silicon die attach. The gold silicon die attach is going to vary in density because gold is much heavier than silicon. So you're going to have some densities playing against you there when you do that type of inspection. In this case, we thought we had noticed severe voiding, but again, we weren't sure due to the density. We decided to go ahead and cross-section this device and get some good eyes on what we're seeing. You can see what the cross-section revealed here is that we did have good die attach on the left-hand side of the silicon die. But to the right side, we see a lot of voiding. At this point, EDS is done to see if that's our epoxy that went through, if it's an epoxy-rich area that's lacking silicon and gold. But you can see they don't have as good of a attach as they would have hoped. I must love X-ray. I have a lot of good X-rays examples. So here's another thing talking about density. So on the top left-hand side image, you have an X-ray. You see the silicon die is actually that square shape there, and around that is the die attach. The voiding seen underneath the silicon die seems to be pretty bad, but was mostly concerning was the density change of the die attach right outside of that square. Once we delidded this device, and put it into the SEM, we were able to see that the die attach was actually peeling away from the device itself, from the silicon die itself. All right, so plastic encapsulant voiding. This is a great example of why X-ray may work in some cases, why it may not, and why CSAM may be a better choice for doing your non-destructive screen. So you have your X-ray image on the top left-hand side. The device looks great. We're not seeing any plastic molding concerns, no bonding concerns, no lead frame concerns, and no die concerns. When we put this part into scanning acoustic microscopy, we noticed a lot of interference, more so that we've ever seen. Not quite sure what was going on here. We knew it had to be in the molding because we didn't see anything in X-ray, nothing that was dense enough to be picked up. The through scan image, the far right image on your screen, is a through scan image. You can see the bubbles that are in there. Again, we weren't quite sure what was going on. It was something kind of odd. But again, we cross-section the device because we are a destructive lab and sometimes we like to take things apart. So next slide. We cross-sectioned it and this is what we got. A ton of plastic voiding. This is gross. This is something that should have been brought up with the manufacturer. Several causes could have led to this, you know, abnormal molding conditions, poor plasma cleaning, processing, improper storage of the molding compound, or even a contaminated environment in which this was built. But the story here is that not all non-destructive testing will get you what you need, but one or the other may. And I got a couple more for you. All right, so stacked die construction. Stacked die is fairly new in the industry. It's not really well covered in the MIL standards just yet, but it's super cool. It's sometimes called 3D technology. The top left-hand image there is an X-ray. You can see the multiple stacked silicon die. When we cross-section this, again, you're able to see that there's 4 silicon die that are bonded. The silicon that's placed between those bonded elements are actually spacers so that there's enough room to bond each individual silicon die. The key when you're doing this type of inspection is you do want to do a cross-section on a stacked die because you want to see how much clearance you have between bonds. To bond something like this is, I'm sure, very difficult. And that leads us with copper bonds, but I'll stop there and see if there's any questions. None? All right, do you want to cover copper bonds?
I can. So the copper bond wire, next slide. So as Rachel mentioned, it is really important that we decap it appropriately. The copper bonds are susceptible to chemical attack and can be, yes, we can chemically decap the part, but it's a lot of acid. And in case of laser ablation, you ablate it to maybe 80% of it, and the last 20% is a little chemical etching, and that allows us to not have the bond wire as much attacked. We probably have 95 to 97% of the bond intact, very, very little attacking going on when we use the laser ablation and chemical decap. Yes. So but laser ablation also is a technique and art. If you don't have the right settings for the laser ablation, then you will either excessively burn or actually you'll burn the bond wire. So we have to be very careful how we do the laser ablation. That's one of the reasons why an X-ray before laser ablation is very important, and making sure that we know what the depth where the wire is. And if it's too much of a laser ablation, it also attacks the die surface. So not only the bonds are attacked, but the die is also attacked. You'll practically destroy the device. Next, please. So in terms of chemical decapping, we can do a pure acid decap, no laser ablation whatsoever, or we can use laser ablation and acid. But it is not pretty simple. The decapping of a copper bond wire is a very, very delicate process. So even if you laser ablate the part up to 80% and start using the acid, the sensitivity is so the bond pull and the likes of it. In case of gold wire, there's a lot of forgiveness because you can over etch it and still take care of all the molding compound. In case of copper bond wire, the forgiveness is very little. So you got to use the right acid, so you're able to take the most of the molding compound. The temperature is also critical. You have to have the right temperature. In case of chemical gold wire, you can do a 25 degrees C chemical etching, no problem. Maybe a minute over, 30 seconds over, no harm done. In case of copper bond wire, you absolutely have to have the right formula, the right temperature to be able to get the right amount, to get the moldy compound out before it starts to damage the wire. And there's a drip and submerge method that people use. And above all, one of the most important items is the rinsing process. You have done the chemical etching, you have done the laser ablation, the chemical etching, but if you don't have the right rinsing formula, you will not get the chemical out of there. You will not get the moldy compound out of there. If you don't have the right rinsing methodology, if you don't have the right agent, then it becomes, you will harden the moldy compound that remains up there, and you'll not be able to do either your visual or your monochrome.
And one thing to note there is MIL Standard 1580 Revision C, now that they're including coppers into requirement 16.5 for plastic, they do require, when you're doing decap, to fully expose the full length of the bond wire, the copper bond wire, when doing decap, which is different than golds, because in golds we're exposing 75% of the wire. For copper bonds, we will expose the entire length all the way to the stitch. So that is, again, why rinsing is so key.
Absolutely. No, that's a very good point. This is one of the results of our chemical exposure. And look at that, such a beautiful stitch bond, not a single piece of molding compound left on the wire, underneath the wire, on the pad. Next. So somebody asked the question, how reliable is copper bonding? And if the copper bonding is not done right, so what it is, it's in case of copper, it is so rigid that when that when the bond wire comes in and hits the pad, it comes in extremely hard. There's no cushion material available there. In case of gold, there is. Gold is a lot softer than copper is. And so when that copper bond wire comes on the bonding pad, if the process is not right, you'll see bond pad splash, your aluminum splashing on the side. So this is what this is showing.
Yeah, so your ball bonds are much harder to scrub in, and they create a much larger splash. And there's some concerns of the die cracking underneath that because of how difficult that process is.
And so that's a very good point. If it comes on really hard, if underneath the pad there's an active circuit, if you cause a crack on that active circuit, that part will either fail during electrical test or it will fail during reliability testing. So yeah, it's critical that the bonding process be just right and not destroy any circuit underneath it. And this is a cross section of the stitch bond, and it's really important to have a good cross section, and because it tells you the formation of the stitch bond again and the wire thickness for inspection purposes. And so what are the concerns with the copper bond wire? It easily oxides in air. Copper absolutely oxidizes quicker, and that's the reason why when a copper bond wire product uses a different molding compound, it uses a lower pH content in the molding compound. So copper is harder just making the bonding process difficult. And we talked about it could attack the active circuit underneath it, potential yield and a reliability problem. And typically halogen-free special molding compound needs to be used because of the oxidation of the copper. So the molding compound is special molding compound. And the concerns are the bond pad aluminum deformation, the splashing, the cratering, the cracks that we talked about, the copper bond wire, interface corrosion, and intermetallic. The intermetallic in the copper and the bonding pad material, whether it's aluminum or whatnot. And so this is some more examples of aluminum splash. And this one shows that the bond lifted the majority of the pad and some residual silicon, which is really a no-no, because that's if when you do a bond pull and you see residual silicon up there, it means that the bonding was not proper. Or if you see majority of the pad being lifted, that's not a good. You want that during the bond pull test, you want the wire to break at a certain place by the neck or something like that. You don't even want it to be breaking in the middle. But if it doesn't break and it pulls the whole or some portion of the bonding pad out, that shows a fundamental developmental issue, the design issue of the process of gold bond wire.
Yeah, that's a good case.
This is just another example of bond lift with little to no force. In this case, there was a bond pull done and it just came off, and that just shows that the intermetallic between the wire and the pad never really happened. It was just practically sitting up there. There was not a good scrubbing motion going on, and it's just a bond wire practically sitting on the pad making contact, but obviously you have a lot of intermittency during actual device operation.
Yeah, you have in your previous slide, you had a clear case of overbonding, and in here is what we consider underbonding.
Underbonding.
Where it's just sitting there and there may be some chemical residues there that left it dirty, if you will, and caused it to perform the way it did at bond pull.
Or the scrubbing was not done right.
Fair enough.
Yeah.
Great.
This shows some of the other problems. There's a crack or broken stitch bond, and there is an actual case or cases in which the delamination on top of the wire was attributed to the actual failure of a stitch bond that resulted in a field failure. So if you go to TI has written some really, really good papers on copper bond wire, and one of the things they talk about is delamination by itself is not necessarily a problem, but when it comes to copper bond wire, it may be a problem, because that delamination on a copper bond wire, there's very little forgiveness. That moisture seeps in, goes into the package, and causes your corrosion effect with the copper. In case of gold, there's no such chemical reaction going on. In case of copper, there is. And so delamination is one cause of it. Non-bonded region in the critical bond interface is another. A CTA mismatch between the gold wire and the pad is another reason for having cracked or broken stitch bonds. Next. Want to cover real quickly?
Sure.
And we have.
Are we running over?
No, we are not. We have 19 more minutes, and let me check if there's any questions. There are 2 questions. Let's just address those. How accurate is X-ray for determining bond wire material? Do different alloys of copper affect results with trying to determine between copper and gold bond wire? And all I can say is copper has got different radio density than aluminum does. So is X-ray effective? It is only effective if you have a known good device that you can match it with. In case of it's not always an experienced engineer or a technician probably can tell whether it's copper or not using an X-ray. So there is a 20% of the time that it's not possible.
Yeah, I mean, gold is obviously more dense than copper. An experienced technician will be able to look into the X-ray and say, okay, this is dense. I'm 85, 90% sure it's going to be gold. You can never really be 100% sure because the wire size is going to have a play on density, so that is going to skew some of your thinking, if you will. But aluminum, you're not going to see that in X-ray. So if you have a skilled tech, I would say a good 90+% of the time they're going to be able to determine that. Again, it's not 100% foolproof.
All right, thanks.
That the last question for that?
That was the last question, and we practically have maybe 10 or 12 more minutes, and then just do a wrap up for that.
Okay, I just got to make it through flip chips, and we're almost there.
All right.
All right. So flip chips, MIL Standard 1580 Revision C does now reference flip chips within section 16.5. Essentially, the test within 1580 can be customized to determine a test flow. There is no specific paragraph right now for flip chips. Hopefully, eventually, there will be. In the case, and since now we don't have criteria, we propose a two-path approach. All samples will undergo the non-destructive testing that is seen in the left-hand column there. Then what we'll do is we would split up half the population so that half will undergo path 1, which is some type of destructive testing. The remaining population would go through path 2, which is another approach to destructive testing, which includes your cross-section and that kind of stuff. Next slide, please. So some of the non-destructive testing for flip chips that may be applicable other than external visual would be an X-ray inspection. With X-ray, you're able to look internally to the part. In this case, you're able to see the capacitors or resistors that are sitting around the chip. You should be able to inspect for the solder bumps, looking for voiding. You can also look at the solder balls to the backside or the external to the package, looking for voiding as well. Another non-destructive technique would be acoustic microscopy. It's a great technique to look at the underfill of the BGA, of the flip chip. And you can also, if your CSEM is good enough, you can look at some of those solder bumps, if you will. That gets really, really tricky, and it could be in-depth inspection, but it could be done. So we're talking about path 1 type testing now. We start destructive testing with flip chips. At this point, if it's a metal lidded flip chip, we would remove that metal lid, and you're able to expose the internal workings of the device. The top left side image there, you can see the silicon die with the underfill material still attached. Don't forget, these are called flip chips for a reason. The die is obviously flipped the opposite way. So in that top left-hand image, you're seeing the back side of the die because the active circuitry is actually still solder bumped down to that substrate. In order to do an inspection of that active circuit side of the die, you essentially got to use a chemical process or float off that active portion of the silicon die, pull it off, and look at the active circuitry. When you do that, you're able to look at your die markings in the metallization structure itself. Also, when you remove the lid, you're able to look at the passive components underneath. In this case, you can see the cap that was many caps that are internal to the device. Next slide, please. Path 2, that consists of the cross-section processing now. What you can see there is the top left-hand image is the device and package in cross-section. The metal lid is still intact. You can see the underfill and the lid attach, as well as the substrate and the solder bumping, as well as the die internal bumps. It is good to look at the internal structure and the alignment of those internal solder bumps, because after all, it is what powers on the chip. Obviously, the external bumps too. But also in cross-section, you can, after delid, you could pull off the capacitors and do a cross-section on those, and do inspections to EIA 469, because those are all part of the DPA for a flip chip, or at least we think that it should be. Here are some more images of what the cross-section will do for you. In addition to solder bumping, in flip chips, we have things called CGAs, which are your column grid arrays. You can see that on your right-hand images there. And again, cross-section is a great technique for this type of device because you want to look for any misalignments, any cracking, anything of that nature. You can also look at PCB via substrates also. Do you have any questions there on flip chip?
No, I don't. Today we had a meeting on 1580C with CE12, CE13, C11, and JEDEC members also attended. So one of the things is that 1580 Rev C does not really cover flip chip right now. One of the consideration is that we need to put it up there. So the task team has been formed. Mike Azzolino from Aerospace Corp is driving that. Integra, High-Rel Lab, and a couple of other, Oneida, also are going to participate in establishing the flip chip requirement. Lockheed has had quite a bit of experience in establishing some of the requirements with us in the past. So we're going to reach out to them. So flip chip is relatively new in terms of what their actual requirements are. We have been doing flip chip DPAs for a long time, but it's not formalized, and it will be formalized relatively quickly. And as far as the MIL-STD 1580C is concerned, Rachel and I, again, in the same meeting, attended along with other labs, other users, wide spectrum of people from NASA to Lockheed to Honeywell to Aerospace Corp to the various labs to Raytheon to Boeing, and we're starting to look at what are the nuances that we don't like about Rev C changes that is either driving costs higher or not buying us anything. At the end of the day, it has to work for our customers like you. Obviously, that's why you're here, to listen to what are the various issues related, or how does 1580 work. So Rev C does have some issues, and it's going to be addressed. Probably take a couple of years to be the committee's work, but we're going to start addressing it.
I like that there's conversation this early on.
There's a conversation going on.
Yes.
And the various labs are involved.
Yes.
And the users involved, the DOD is involved, DLA is involved.
Yeah.
So I really like that idea.
Yeah, me too.
Yeah.
If we have a second, I can cover a few of the changes, and then we can open it up for full-on questions if you're game.
I'm game. Let's see, I'm just going to look for time. So literally you have 3 minutes and 4 minutes.
I need less than that.
Okay.
We'll be good. All right, next slide there. So Sultan spoke, he mentioned some nuances with 1580. There are some nuances, but there's also some good stuff that came out of it and some good clarifications. We will be working on further clarifications that will just make this standard more robust and more usable to folks like us. So in general, each section underwent some type of change. It may be as minor as a paragraph number change, or it may be as complex as adding a whole new section. I really strongly recommend that you folks go out and look at Rev C because there's some good stuff in it. For one, internal PMA, PMI. It is now called out in each commodity. So if a capacitor needs internal PMA, it's called out in that commodity paragraph. So refer to those commodity paragraphs if you are wondering if it's required or not. IGA failure criteria. I have 1580B in comparison to 1580C up on the screen. Just some minor clerical changes there. As I mentioned early on, copper bonded plastic devices are now covered in 16.5. Notably, copper and silver shall have their entire wires, including the stitch bonds, exposed. Sultan and I talked about that earlier when he was going over copper slides. Also, they'll meet the requirements of gold, and they've included wire bond shear for plastic devices. One important thing to know, we talked about dye penetrant after acoustic microscopy testing. 1580 Rev C now calls out dye penetrant within requirement 16.5. They do have a note in there. Some folks, MIL standard 883 test method 1034 is for dye penetrant of PEMs, if you will. We are still using that criteria. However, instead of applying pressure to do the dye pen test, we'll be doing vacuum for 5 minutes. So that is a deviation that's within the MIL standard 1580. 883 1034 dye penetrant inspection is now done a little different than 1580. So that's notable. Requirement 18.5 for resistors. They now added back in cross-section of one sample. Back in 1580B, they had stripped that out. Those are just some of the most notable items, but again, as I mentioned, every section underwent some type of change.
Thanks, Rachel. There's a question, last question is from Manny, says, are you seeing a lot of failures with multi-anode capacitors?
Oh, great question. That's a great one. And I didn't even get to cover that, and I'm glad someone brought that up. So single anode capacitors are covered in 1580 Rev C, and we do destructive testing, which is a cross section, which is great. But now 1580 Rev C included multi-anode capacitors, and the criteria for that is basically an external visual inspection. So we're not doing any destructive testing there. Our plan is to add that in, to have some discussions, which we did today in the meeting. Have we seen failures? We have 4 anode type capacitors, but mostly in X-ray. And then we verify in cross-section like a cracked anode riser.
So his other comment was, one of your competitors says they're seeing a lot of cracking, but I don't know that you're having the same experience. And our answer is, our experience is no different than our competitors. So it's, we are, you know, we are seeing it also. Let's see, were there any more questions? I don't see any more questions. Let me go up there one more time.
You guys are gonna let me off easy. I'll take it.
Well, thank you very much, everybody. I hope this was a good experience. It's a little bit different than just doing a webinar. It's a little bit longer. It takes 30 minutes, you know, a little bit extra time, extra 30 minutes. But it allows you guys to ask the questions, and allows us to answer real time the answers to your questions and any subsequent questions there are. As usual, please send us an email. You know, Rachel's email address is there, her phone number is there, my email address is there, my phone number is there. We have, if you go to our website, there is a logo up there that says technical hotline. You can very simply put a question up there, and it'll come to us, and we'll be able to respond. And there are, you know, a few thank you notes coming in saying, hey, thanks on the chat, but I think we did good.
Great job, my friend. Thank you for co-hosting with me today.
No problem. Great. Thank you very much, everybody.
Thank you,
Have a great
guys.
evening. Are we off?